Hey there, everybody. It's Mr. Sheeline. Welcome to this Unit 3.2 notes. We're going to be looking at Newton's second law. So I mentioned in class that for the most part, these sets of notes are going to be pretty short. So these notes are going to pretty much just cover, they're pretty much just going to cover, what the law is, but then for the most part, the rest of it is just applying it. Because again, the first and third laws are very much conceptual based. The principles that you follow and that are observed. The second one is taking those principles and more or less putting it to calculation. So let's get right to it. So here is a layout of the three laws again, just in case, all three set of notes here, or at least all three sets of notes where we are discussing each particular law. I'm going to include the three laws. So we've gone through the first one so far. And remember, the first one is if the net force acting on an object is zero, that object maintains its state of rest or constant velocity. Okay. Second law is an object accelerates in the direction of the net force. The acceleration is directly proportional to the net force and inversely proportional to the object's mass. So that's just to say that acceleration is equal to force divided by the mass. Okay, that's our acceleration. But we don't write it as that way. Well, how we write it is actually force is equal to mass times acceleration. Just because we want to know what the force is. Because a lot of times, especially when we're talking about falling objects, we already know what the acceleration is. Third law. For every action force, there is a simultaneous reaction force equal in magnitude but in opposite direction, which we'll get to later on, not in this set of notes, but later on throughout this unit. And then remember, we use newtons in order to measure this out. And where newtons are, it's a derived unit. It's a derived unit of kilograms times meters per second squared. Okay, so an object accelerates in the direction of the net force. So that's stated within the law. So the acceleration, again, is directly proportional to the net force and inversely proportional to the object's mass. Another way of saying that is this guy right here. It's this guy right here. This equation is what Newton described and what he specifically describes in his law. But when we apply it, and when we're, again, trying to solve, for the most part, this is what we're using. Now, that's not to say that we're not going to have questions where we're going to have to use this, because there will be questions where you'll have force, and it'll equal whatever x, m will equal y, but then we don't know what acceleration is, and we're going to have to figure that out. Okay. So there'll be ones where we'll have force and acceleration, but we don't have, mass, and we'll have to figure out what mass is. So, okay, acceleration increases as force increases. Acceleration decreases as m increases. And the same thing is the inverse for both of them. Acceleration decreases as force decreases. Acceleration increases as mass decreases. Okay, so both inversely are true for each separate idea here, but they are they are not mutually exclusive. Ooh, actually, I'll retract that, because there's a lot of times, and I'm in the middle of making notes. Maybe I shouldn't have said that. Forget I said that, because my brain just had a brain fart, and I think I applied that wrong. So forget I said that. Okay. So Newton's second law, remember, force is a vector. You've got to remember that. Force is a vector. Direction of our forces are super duper important. Okay. We have to mark our answers with directions and with the proper units. Not only that, when we are drawing our free body diagrams, which you still, even though we're doing calculations, free body diagrams are even more important here than they were just practicing in the first law or with the first law. If you have two forces being applied on the same plane, You have to know which directions are going, because you have to attribute something as positive and something as negative. If you don't, you're going to wind up with the wrong answer. Either it's going to be too big or it's going to be too small. Sometimes it may be negative when it should be positive. Just depends. Depends on what you're solving for. But anyway, remember, force is a vector. Direction matters. So, and that's pretty much as far as that goes. So I add this little section here about weight. So just so you know, like when we're measuring force in newtons. Weight is a force, or sorry, weight is a measurement of force. Weight is when you step up on a scale, you're measuring how much your mass is affected by gravity. Okay, so it'd be whatever your mass is, because remember, mass doesn't change. It'd be whatever your mass is times the acceleration due to gravity. Okay, so easy peasy, right? Force would be, now there are scales that do scale in newtons. There is a somewhat easy conversion to go from newtons to pounds. In fact, I think you're going to be reading about them in that little reading handout that I gave you. But anyway, your weight stepping on a scale is no different than that measurement of pounds is just another form of measuring a force. Okay, your weight is a force. Okay, so here as I list, F equals m times a is describing how we measure weight here on Earth, where mass is equal, or m is equal to mass, and acceleration is equal to gravity. Okay. Well, that's weird. That shouldn't be in there. No, go back. What are you doing? Hey, wait. Whoa. Hold up. Sorry, I don't know what's happening. Okay. I think I've got a blank. Okay, come on. Yeah, I think that's just a blank. Oh my goodness. Just give it a second. Oh, it's the video. That's right. I almost forgot about the video. I'll link to this video. I completely forgot about this video. I'll link to this video in the Google Classroom here. It's a super short video. It's a nice little experiment put on by a couple of college professors. But I'll link to this in this Google Classroom assignment or the material. Okay, that's what that was, and that's why all of a sudden it's really slow. Okay, let's try this again. Okay, so let's now try out these check your understandings. So the mass of a hot air balloon, including the passengers, is 900 kilograms. The density of the air inside the balloon is adjusted by adjusting the heat output of the burner to give a buoyant force of the balloon, or on the balloon, of 9,900 newtons in the upward direction. Determine the vertical acceleration of the balloon. Okay, so let's pause the video here, try this on your own, and then after you try this on your own, then come back and then we'll go through this little example. Okay. Okay. So now this one is a little tricky, but at the same time, it's really not. So let's first identify what we know and what we don't know, and then we can start drawing some pictures here. So, okay, we've got the mass of the hot air balloon. So the mass is going to be equal to 900 kilograms. Okay. We also know the density, blah, 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 that there is an upward force already. So there's an upward force, and that upward force, don't want that. The upward force, so I'm going to put F up. F up is going to be, actually, and what we can actually call this, it's not just an up force. Because it's an air balloon, this is going to be the applied force. Okay, so this is our action force. So our action force, our applied force here is going to be 9,900 newtons. Up. Okay. Oh boy, that is a, geez. Okay, so what don't we know? Well, we want to know the acceleration. We want to know the acceleration here. Now, there is something else that we don't have here, and this may not have been terribly obvious to you, but before we get to that, let's maybe draw a picture first. So when we draw the picture, let's just draw the picture of what we have. So we've got this hot air balloon. Yay, hot air balloon. Okay, now, normally I would draw with all kinds of different colors to show that's a hot air balloon, but limited on time here and also limited on, I guess, processing power. This poor little thing could barely chug along these notes. But anyway, so we've got our hot air balloon here. And our hot air balloon, we're going to say let's say the mass, just because most of the mass is concentrated here, we're going to say it's right here. It has a downward, in this case, mass. We have a downward mass of 900 kilograms. But we do have an upward force here. We do have an upward force, an applied force of 9,900 newtons. Okay. We don't have anything to the sides, and this is all that we have. Now, hopefully you see it. You can see it right now, that maybe we're missing something. So what we may be missing is that we don't really have like terms here. What do I mean by that? Well, take a look down here. Is mass the same thing as the force being applied? Or at least are they the same units, or are they measuring the same thing? No, they're not. So how do we get to the point to where they are showing the same thing? Easy peasy. We have to know what the downward force is. Oh my goodness. How do we know what the downward force is? Easy enough. We know the acceleration in the downward direction. We have the mass. We can find the force. So we know that force is going to be equal to mass times acceleration. So we can quickly understand what the force, the downward force is. And our force is going to be equal to our mass, that's 900, times 9.8. And if we punch that in the calculator real quick, so 900 times 90, or 9.8, we should get 8,820 newtons. This case down. Okay. So now we've got something we can work with. Okay. See, this is why it's always important to always draw a picture. And if my voice is cracking right now, and if it sounds really bad, like if you're having a tough time listening and if it's popping, I apologize, because again, this is a processing problem. But if it's still working just fine and you can hear me just fine, perfect. Okay. So we've got the downward force. We're going to put that. So in this case, it's not just the downward force. This is the force due to gravity. Okay, so it's 8,820 newtons. Okay. Come on, I want the eraser, please. Oh, for Pete's sake. Jeez. Okay. Need more room on these. Check your understandings. Okay. So we've got the applied upward directional force, and now we've got we have the downward force due to gravity. So what do? Well, remember what we're looking for here. We're looking for the net force. That's what we're trying to solve here. Well, at least we're trying to know what the net force is, because in order to find the acceleration and to know which direction it's accelerating at, we have to find the net force. So how do we find the net force? Well, the net force is going to be just in this case, it'll be the applied force minus the force due to gravity. Okay. So now we did it this way just because we should expect, seeing what the forces, the magnitude of our forces, and that it's already saying that we are moving in the upward direction, that we should assume then our upward direction is our positive direction. So that's why we set it up to where applied is subtracted from the gravity is subtracted from the applied here, or applied minus gravity. So if we take 9,900 minus 8820, we should get the net force. Oh my goodness, wow. Our net force here should equal 1,080 newtons. And not just 1,080 newtons, 1,080 newtons in the upward direction. Okay, so I'm going to get rid of all of this and just keep what we need. Okay, let's go. Eesh. Oh boy. So again, we've got force due to, or sorry, not force due to gravity. We've got our net force now. So we have our net force, and our net force is going to be equal to 1,080 newtons in the upward direction. We do have our mass. Okay, we still need to use mass. Okay, because that still plays a factor here. We have our mass of 900 kilograms. What we need now is we just need acceleration. Okay. And our equation here is going to be F is equal to m times a. So we're going to rewrite it up here, but we're going to have it a is equal to F divided by m. Acceleration is equal to 1,080 newtons divided by 900 kilograms, and we are left with acceleration equaling 1.2 meters per second squared in the upwards direction. Okay. So I know that seems like a lot, and I know that seems like, Mr. Sheeline, how could we have even possibly come up with that kind of answer? How could we have figured that out? Where this stems from is that you've got to draw pictures, and you've got to look for those like terms. And I know I didn't explicitly talk about those like terms, looking for them, but that's why this is not a graded assignment as of right now. Like this right here, this check your understanding isn't a graded assignment. And two, it's all part of the process here. It's needing to see that context, to see that, I have a force in the upward direction, but I've got mass in the other direction. I don't think I can do anything with those two. I need to change something to another thing. It's no different than if you're given, velocity in one direction and then acceleration in the other. You have to change that acceleration or apply that acceleration in a particular formula to solve for it. And that's kind of what we did here. Okay. So draw those pictures. That's my message. Draw those pictures. Draw those free body diagrams. Okay. So let's take a look at number 2 here. A net force of 58 newtons in the westward direction is applied to a water polo ball that has a mass of 0.45 kilograms. Calculate the ball's acceleration. So pause the video here, and then we'll come back to it. Okay. So let's take a look here. So 58 newtons to the west is applied to a water polo ball with a mass of 0.45 kilograms. So let's write what we know and what we don't know. So we know we have force here, and force is equal to 58 newtons, specifically to the west. And we have a mass. We have a mass of 0.45 kilograms. Okay, calculate the ball's acceleration. So we do not know acceleration. Whamp, whamp. Now, hopefully you can see that this is actually going to be way easier than the last one. So the last one, and we need our F is equal to m times a. So we're solving for acceleration again. Easy peasy. This one is we're going to rewrite the equation up here, but solving for a. So a is going to be equal to F divided by m. And we can just start solving. So a is equal to 58 over 0.45. It's newtons, kilograms. Okay. Oop. Our acceleration here is going to be equal 58. Oop, come on, calculator. 58 divided by 0.45. And what we're left with is 100 and, we'll say 29 meters per second. Now, we're not done yet. Meters per second in which direction? To the west. Okay. Now, if we wanted to draw a free body diagram of what's happening here, and this is the answer, by the way. We've got the answer. If we wanted to draw a free body diagram of this guy, it's easy peasy. It would just be this. You would have your circle here, you'd have your dot here, your origin. 58 newtons. Now, so a net force, just think of it in this way, though. Like, this is all we're told. To a water polo ball, we're not told if it's in the water. We're not told if it's flying through the air. It's probably being flung in the air. So there would be like a gravitational, force as well. This is the applied force. If there was no air resistance, and this would be it. If there was air resistance, we would say this. There wouldn't be a normal force because it's not on anything; it's in the air. But realistically speaking, the way they describe what's happening here, all we have is really just this. That's all we have. Need more specifics in this case to know what's happening. Then number 3, it's in an extreme test of its braking system under ideal road conditions, a Toyota Celica traveling initially at 26.9 meters per second south comes to a stop in 2.61 seconds. The mass of the car with the driver is 1,180 kilograms. Calculate first the car's acceleration and then the net force required to cause that acceleration. So deceleration. What kind of force was required to get it to stop over that time period? Okay. So pause the video here. Try to see if you can calculate this and figure this out on your own. Okay. So as always, let's just write down what we know and what we don't know. Starting with the first question here. What is the car's acceleration? So give me that green. So it looks like we've got initial speed. So we have an initial speed of 26.9 meters per second to the south. We also do have a final velocity. It's 0. Final velocity is 0. We have time. Time is going to be 2.61 seconds. And we have the mass of the car, which is 11180 kilograms. So we don't need the mass right now to calculate the car's acceleration. All we need, obviously, to calculate the acceleration is just the acceleration equaling final velocity minus initial velocity all over time. So acceleration, plugging all that in, it's going to be equal to 0 minus 26.9 over 2.61. So our acceleration over this time period is going to be a negative, 26.9 divided by 2.61. It's going to be a negative 10.3 meters per second squared. Okay, and specifically, if a car is going south, that means then if our acceleration here is negative, what's opposite of south? North. Okay, so now we have acceleration, so we can get rid of pretty much everything. So negative 10.3, remember that, negative 10.3. So we have an acceleration of negative 10.3 meters per second squared to the north. Okay. We have time. Well, we don't need time right now. We have mass. Come on, give me the pen. We have mass of 1,180 kilograms. Now we just need to calculate the force needed to accelerate at this rate. What is that force? So hopefully you can already see this is going to be F is equal to M times A. So let's just write it out. So force is equal to negative 10.3 times 1180. So the force needed is going to be 10.3 times 1180. It is going to be 12,154 newtons. Now, we're not done yet because this is a negative. So it would be a negative in the northern direction because, again, if it's a negative, it has to be in the northern direction. And we know that because we know that the brakes being applied is going to it's going to oppose the force propelling the car, in the southern direction. To bring it to a full stop, it has to be the opposite direction. Now, do we want to leave it negative? Not really. We don't want to leave it negative. So realistically speaking, because we already know that the car is going to be halting at a stop, or we know that it's going to be coming to a stop, we shouldn't keep this negative. It should be, in this case, we don't have to. You can have it 12,154 newtons in the northern direction. So we already know it's going to stop. We already know that the acceleration is negative, that the acceleration is in the opposite direction. So we already know the direction of our force here, so we can keep it positive. And so we would have a positive force of 12,154 newtons to the northern direction. Okay. Oh, and that is it. So that is those are all of the check your understandings for the notes here. So like I said, a pretty fast set of notes. I'll post the video again on the Google Classroom. So go ahead and go back, just take a quick peek at that video. It's like, I think 4 minutes long or something like that. Other than that, if you don't understand something about about these problems, make sure you get a hold of me. Just remember, we're going to be grading that worksheet that I handed out to you guys. For A days on Monday. For B days, it'll be on that's right. We won't have school on Tuesday. Go election day. Oh, God. I'll get to you B day kids about what to do with that. But anyway, if nothing else, I'll see you guys later, and I'll see you in the next one.